by Microsoft DC Metro engineering site. Today, we have the pleasure of having two speakers, Dr. Suresh Kumaar Jayaraman and Dr. Pak Wen. Our first presenter will be Dr. Suresh Kumaar Jayaraman, who is currently a postdoctoral researcher at the Robotics Institute at Carnegie Mellon University. He attained his Master of Science and PhD degrees from the University of Michigan in 2018 and 2021, respectively, following his Bachelor of Science from Anna University in India in 2013. Before joining CMU, he held postdoctoral positions at Cornell University. Dr. Jayaraman's research revolves around the development of trustworthy robots for seamless human-robot collaboration and teaming. His current focus lies in group human-robot interaction with an emphasis on explainability, implicit communication, and fostering trust in robots with groups. So thank you for being with us today. The floor is yours.
Thank you very much, Professor Saiti, for the wonderful introduction. Okay. I'm still in a different slide, I think, but I hope people can see my title slide.
Yes.
Okay, great. In today's talk, I'd like to, first of all, briefly introduce my overall research interest and what I've worked on so far, and then go in a little bit of detail more on my most recent work, which is on developing some techniques for improving transparency in human-robot teams. So my research is primarily motivated by this objective of developing trusted and trustworthy robot collaborators. And there is like a slight nuance difference between those two, whereas trustworthy is mainly focused on, the attributes of having to be trusted, and trusted is actually like whether they're actually being trusted, like measuring their actual trust, either through like behaviors and other factors. But maybe they shouldn't be too trusted because robots are not all capable of everything, and they might also make mistakes. So we should probably not be too trusting of those robots too, because while a lack of understanding can lead to ineffective collaboration between humans and robots, misunderstanding and overestimating the robot's capability can also lead to potentially dangerous situations. So my research is primarily focused on developing safe and fluent collaboration between humans and robots. And for that, they must each understand each other's decision-making, which could be a result of their individuals, like the humans and robots' goals, their preferences, or capabilities. Transparency, explainability, and communication are key to understanding each other's decision-making. So this is kind of like the guiding force for my research. And my research right from my grad school days can be broadly categorized into three areas. The first is understanding the human's behavior. And the second area is robots understanding the human behavior, human behavior modeling. And the third is coming up with interactive policies for the robots, keeping in mind how the humans that they're interacting with would behave. My initial research mostly focused in the autonomous vehicle domain, where I looked at how pedestrians interacted with automated vehicles when the vehicles were communicating through their implicit behavior, just through their motion. How pedestrians trusted these vehicles, how they behaved when these vehicles were, for example, behaving aggressively or defensively, and how we could actually, measure their trusting behavior. How would pedestrians react when they're actually, trusting the vehicles, whether they are stopping for it, whether they, jaywalk, etc. And also use these user studies. I conducted a lot of user studies and virtual reality simulations in real world. Also, as you can see, and also use this user studies to come up with the data or while augmenting it with real world data sets to come up with pedestrian behavior models, particularly when they are interacting with the autonomous vehicles around crosswalks. I also did a little bit of like driver behavior modeling, particularly their trusting behavior. How can you estimate driver's trust from how they're engaging with the automated vehicle, how much they're monitoring the automated vehicle, their gaze behaviors, and some external factors. So using these models of human behavior, I developed like policies, robot policies, um, that are interactive in the sense that they predict how the humans would interact with the robot and use that to come up with both safe and trustworthy controllers. In the case of pedestrians, they are like mostly focused on the navigation. And in the case of drivers, it was mostly focused on explainability, coming up with explanations such that it would moderate or calibrate the driver's trust. For example, if they really trusted the vehicle or over trusted the vehicle, it would say that, oh, you shouldn't over trust me. I don't have the capability in the next road segment to drive by myself, so you need to help me. Or when they're under trusting, it will reassure them saying that, oh, I can, handle myself, so you can focus on your other task. While most of my prior research focused on this in situ collaboration or like during the actual collaboration activity, it all more importantly focused on the dyadic interaction between a human, a single human, and a single robot. However, this is not how robots would be interacting or collaborating with in the real world. As you can see, like a robot, hospital robot interacting with a group of, healthcare workers, or a robot interacting with a group of emergency response personnel. Real world situations always have these group interactions. Um, and so so the question then becomes, how can we actually, how can the robots um, explain their decision making to a group of people, that too in a proactive manner, because in situ explanations may not always be very helpful. They might take a lot of time. It might be too late for the robot to come up with explanations or give explanations so that the humans would understand the robot's decision making. So how can the robots proactively explain their decision making to a group of people? The paradigm that we use for explainable decision making or explainable reinforcement learning is when the robot has to explain its policies to humans. It can be formulated as a machine teaching problem, where the robot in this case is the teacher, and it is teaching about itself to the human learner. So the robot is coming up with like this lesson plans about its policies, about how it makes its decisions. That is specifically tailored for the to the learner, and it comes up with these example behaviors or explanations. So there are a lot of ways to come like to to give or like to generate these explanations. What I focus on is mostly explanations based on demonstrations, where the robot explains its behaviors in like some sample abstracted environments and use the human's ability, the analytical reasoning ability of the humans to generalize and predict the robot's behavior in similar situations. So the question remains then, how can the robots teach to a whole group using this machine teaching paradigm? And before we answer this, like, why should the robot first of all teach to a group? Why can't it just, teach to each person one at a time? Well, if you consider a situation, like for example, an emergency response situation where there's a group of people who are supposed to, like maybe set up shelters, and they're given a robot to help them in setting up the shelter. It's a delivery robot that can, like bring items to the people, for example. But if they want to use this robot in a very effective way, they need to understand how the robot would make its decisions. They need to understand whether the robot, can go through different rubble, etc. What kind of path it would take, how frequently it has to be recharged, etc. And this can be hard because in situations like this, there are constraints on both time and resources. And that is true for like a lot of real world situations where um, there's not enough time or resources to teach each person individually. So there's a very limited time for everyone to come up to speed on how the robot, to understand how the robot behaves in different situations. But the challenge in teaching to a group of people is that as a lot of you know that you've taught, is it's very hard to come up with a curriculum or a lesson plan that's informative to everyone in a classroom, say for example, or in a group. So it's very hard. And we've seen that explanations are very useful when they're tailored to the person. So in that case, how do we tailor explanations to a group of people? Who do you tailor it to? Like maybe there are a lot of strategies like teachers employ. Like maybe they can focus on the slowest learner. Maybe they can focus on the fastest learner. Maybe they can aggregate the class in some way and try to come up with a lesson plan that like everyone can take something out of it. So a lot of ways to come up with this, but it's very hard to tailor to an entire group. um, and more interestingly, like there are individuals in a group who have different learning abilities, either because of varying prior knowledge, experiences, expertise, or just inherent analogical reasoning ability. So these are some of the challenges that um, are pertaining to teaching to a group of people. And in this talk, I want to talk about one technique that we developed that tries to address some of these challenges. But before going into that, I want to talk about some concepts related to machine teaching that we have employed in general. So the domain that we use throughout that I use, sorry, throughout this work is a delivery task domain, where the robot is a delivery robot that has to pick up an object and deliver it in a particular goal location. It can go through rubble, that's rubble in the environment. It can recharge if needed, and there are various costs and rewards associated with those. And the reward function of the robot is to maximize these different features, which are like going through the rubble. So there's like a negative cost associated with going through like how many like rubble blocks, and there's like a positive reward associated with recharging, and there's like a negative cost associated with taking like the total like number of steps taken to like pick a package and reaching the destination. Um, and the idea is we assume that the human learners know these reward features. So the problem kind of like abstracts to them understanding or trying to know what the actual reward weights are, and trying to deduce that from the observations that they are seeing, the demonstrations that they are seeing from the robot. So the question then changes to what are the informative demonstrations to reveal these reward weights? And the technique that we use to come up with these informative demonstrations is a concept called counterfactual reasoning. So counterfactual reasoning, basically, it consists of thinking of alternatives. It's like imagining what if scenarios. Okay, what if the robot had done something else instead of what if the robot had done X instead of Y? Like, why did it do this? So it's more about trying to understand with alternative scenarios and the consequences for those scenarios. For example, in this case, let's say the human thinks that going through rubble is inexpensive, so the robot would just go through the rubble, which is the red path. That's the human's counterfactual. But in reality, the robot might actually have like a negative cost to rubble, and it might choose to take this two-step detour of going around the rubble. So if the robot knows what the human's counterfactual was, then it can come up with specific examples and demonstration that directly is contrastive to the human's counterfactual. Um, because the robot has access to different set of environments, it can manipulate the environment configuration and trajectories to show to the humans. Similarly, in the next example, if you see, if the human thinks that going through the rubble is actually expensive, then they might think that the robot is going to take this four-step detour. But in reality, maybe this four-step detour is too much of a trade-off, like it's too much expensive, and it's a rather more rewarding to just go through the rubble. So if the robot knows that this is the humans counterfactual, then it can come up with like this specific environment and trajectory combination to show the most contrastive information. And this is because contrastive demonstrations are most informative and really helps the human learners. So we use inverse reinforcement learning. We actually model human learners as inverse reinforcement learners, which is kind of like flipping the switch, and normally how IRL is being used, where humans look at the robot's demonstrations to infer the robot's reward function. And cognitive science supports this model. So initially, on the right is the reward space. So it's the reward weight space that the human thinks the robot has. Because they have no information, they think it's like everything on the surface of the sphere. But as they see demonstration, like we can start removing volume from this surface. Say in this example, this particular demonstration that the robot, the agent has shown, which is the green trajectory, can be generated by all the reward points that is in this yellow region of this the actual reward. Like this is the actual reward point, but all the points surrounding this point in this yellow region convey the same information. This is because you can map the demonstrations to like multiple reward points, and the way that we do it is we like sequentially remove the volume, like by showing multiple demonstrations one at a time. So there is this famous quote by author Anais Lin, which is, "We don't see things as they are, but we see them as we are." So learning is very tailored to the specific individual, and it has to be specific, tailored to a specific individual, because even if they're seeing the same thing, they might take different. There might be different takeaways from the lessons that they're seeing from the robot. So in order to do that, we model the humans what they know. We model the belief of the humans about the robot's reward. So we keep track of what the humans know in order to sample more informative counterfactuals from this model. In this we use a Bayesian particle filter model, where each particle is a hypothesis on the reward weight. And once they see demonstration, we update the weights of the particles using a very specific custom distribution. It's basically all reward points that could have resulted in the demonstration are weighted very high. They're given like a uniform weight, which is on the right side of this plane, and all weights that have like a lower, I would say, like that would not have resulted in the demonstration are given like a low exponentially decaying particle filter weight based on this Bones's distribution. And you can see here how the distribution updates. And this distribution in turn is used to sample the potential counterfactuals for the next set of demonstrations, because this is like a sequential teaching process. You have like the demonstrations are generated in real time based on the previous time steps, the results. Oh, it's potentially blocking, but so the idea is to generate this set of demonstrations to communicate these reward weights a priori, even before the collaboration starts. So this is sort of like a training session by scaffolding different feature combinations, because in this case, there's like 3 reward features. So you can like, teach 2 reward features at a time and then like slowly build upon it, so where you're increasing the complexity. But how can the robots teach this to a group of people? Well, as mentioned before, it can tailor demonstrations to specific individuals, or it can tailor demonstrations to group of people. So the way that it can model group beliefs is like it can identify some sort of like a consolidated belief from the individuals, and we have considered 2 ways on how the robot could do that. One is the common belief, which is basically the belief that everyone in the team has in common, sort of like the intersection of their beliefs. And the other is the joint belief, which is at least the belief that at least one person in the team has. So it's sort of like the union of their belief spaces. So these belief spaces influence the counterfactuals that are sampled to generating the demonstrations, that in turn influence how much they're learning, what information they're gaining from the demonstrations. And that is where we see how the individual belief models versus group belief models can have like a potential impact. We use inspired from pedagogical techniques. This is, yeah, just gonna talk. Yeah, inspired from pedagogical techniques, we use this feedback loop and testing loop, where we not only provide demonstrations, but we also give the users the robot once it generates a set of demonstrations, it identifies the test that it needs to give in order to evaluate whether the learners have understood from the demonstration that the concept or the trade-offs that the robot is trying to teach. And based on their response, it updates their belief model. So this can be considered as like the update step of the Bayesian update. Once it has the updated belief model, and once it knows whether they have answered it correctly or not, it can provide a feedback. It can be like a corrective feedback when they gave like an incorrect response, or it can be a confirmatory feedback to reassure, oh yeah, you've gotten it correctly. But it does this in a sequential manner. So there's like multiple loops. So after they've learned, let's say the first concept, which is maybe it's trying to teach the trade-off between rubble and step cost, it goes to the next concept, which is it tries to teach now the trade-off between battery and step cost. And then finally all three. So it does this in a scaffolded way. And on the right, you can see how the belief space of different people can change. So if it's a team of 3 people and let's say person 2 got it incorrect, you can see how their distribution is very different from person 1 and 3 who got it correct. And that really influences the belief space, like the common and joint belief spaces. So these different belief spaces are in turn used to sample the potential counterfactuals. Okay, so we ran a simulation study to evaluate how these different demonstration strategies affected the learning, and we used it for different types of learners, like proficient and naive learners. And the way that we manipulated the proficient and naive learners is by manipulating how much of weights you need to give to this distribution, that the particle filter distribution, that the custom particle filter distribution that I discussed before, and we use data from prior user studies to know to come up with a set of parameters and sample from that. So we wanted to first check whether teaching strategies actually generate different demonstrations, and it seems like they do. Individual belief with someone with the lowest knowledge, and considering the team's joint belief is likely to have a higher belief area and more information gained consequently compared to the other 2 cases, which is considering the individual with the highest knowledge or the common belief of the team. But does this actually have any effect on the learning? And we considered 2 metrics. The top row is the number of interactions it takes to learn, for the team to learn. And you can see that it's very consistent or very similar across all 4 strategies. However, it changes for teams with higher proficient learners learn quicker, which is not surprising. The more interesting aspect is this interaction between team composition and the strategy. You can see that teams with high proficient learners are able to for teams with high proficient learners, the strategies of common and joint perform better. Similarly, for average team knowledge, you can see that while there isn't significant differences between the strategies, there is joint knowledge. When the strategy is focused on the joint belief space, that is joint knowledge, it tends to a higher knowledge gain compared to the other strategies. And even in this case, you can see that more proficient teams end up having higher knowledge, which is not very surprising. But here also we can see the interaction effect is, I think, the most interesting, where you can see that strategies that is focused on the common and joint knowledge ends up having the most knowledge at the end of the learning session compared to the individual strategies. Whereas individual strategies seems to have less variance. It is more robust to the differences in the proficiency of the teammates, but joint strategy seems to be more informative and more useful in the long run. So to kind of summarize, there is this nuanced interaction effect between the teaching strategy and the team composition, and both of these have to be considered. For example, joint strategies result in higher team knowledge, but individual beliefs have less variance. Joint belief or group beliefs, both common and joint, are better for teams with more proficient learners, And they also have less variance in terms of number of interactions to learn. So if like number of interactions or like the teaching time is a constraint, then you can go for group beliefs. Whereas, like when you want to maximize something, then other strategies might be better. So based on what the objective of the teaching is, whether there's constraints on teaching or learning objectives, or like, you want more robust strategies, you don't know about the proficiency of the learners, you can choose the appropriate strategy. But the more important takeaway is that you need to have real-time adaptive strategies, because these strategies really depend upon like the type of the proficiency of the learners, and they could vary based on the situations. Second, it is not easy to know proficiency beforehand. Since we have done a simulation study, we kind of like predicted it earlier, but estimating this in real time is critical for effective teaching. So in terms of future research, I want to understand what effect this has on the actual team performance, and also try this for more complex domains. We used a very simple grid world domain in this case, but we want to try for more complex domains. And also in a more like long term, try to combine this pre-training session with like an actual in-situ explanations, kind of like filling the knowledge gap that you have in the training session, and trying to come up with more tailored demonstrations based on individuals' goals and necessary information for them to carry out the task, or like, try to augment demonstrations with more verbal explanations, use of LLMs. So which I think is also a very interesting direction to go. So I'm really excited about all these future potential directions that this research can go to. And I'm gonna thank all my collaborators over the years, like across different universities. I'm gonna leave this slide on and happy to answer any questions.
Thank you very much, Suresh. The floor is open for questions. The audience is invited to ask questions if they have any. But I guess I'll break the ice first. So let me just say that this is pretty far from my research field. So I was trying to understand as you were presenting. But one thing that I wanted to ask was, what is with respect to naive and proficient learners, how do you come up with representative percentages for your study?
Yeah, that's a good question, and I kind of like just quickly ran over it. But basically, we have collected a user study from like human subjects user study with like individual learners. So at the end of the session, we would ask them questions. We give them like test, and let's say that we had like 6 tests, and based on how many tests they got correct, we categorize them on like naive and proficient. So if they got 4 out of 6, then like they were naive, like 4 or less, and more than that, it was proficient. So that's how we did the categorization, and we did like grid search to come up with this distribution of parameters for the naive and proficient learner, and you can see the distribution over here. There is an overlap between this, like the best naive learner can be better than the worst proficient learner. And I think we can definitely fine tune how we do this categorization, but this was the way that we did in this case.
Well, thank you very much. So I think time is up for questions. So again, Suresh, thank you very much for being with us today.
Thank you so much.
Hope to see you again soon.